Hey,
Safa, what's going on?
Yo, what's up, Professor?
What's up, Safa? Nothing much. How was your guys' weekend?
fine.
It's good. I actually lied a little bit when I said nothing much. Safa, trying to be humble. I went surfing this weekend. That's what's up.
You went surfing?
Amazing. Yeah, man. 10-foot wave at Virginia Beach. It was fantastic.
Wait, you went surfing at Virginia Beach? What the hell?
Yeah.
Yo,
Oh, you surfing
that's
at Virginia
live.
Beach?
No,
What?
I don't know how to surf.
Yeah, with it, Safa. It's the best thing ever.
Yo, that's kind of live. Well, I actually had like a more than chill weekend too. Like I didn't go surfing, but my friends from Nova came down, so I hadn't seen them in a month. So like that was nice.
That's awesome, man.
Yo, surfing? Yo, that's crazy. Yo, you need to teach me how to surf.
I'm sorry. Just because I'm a math instructor, a PhD student, I can't be cool. Surfing
Nah,
the water on the weekends. I can't have a life.
it's just surprising.
I mean, I
'cause,
don't
like,
have friends. I have waves.
No, I'm just
Waves you don't
surprised.
understand. There's math there.
Oh, sine waves and cosine waves, yo.
Yeah, there's actually like a lot like meteorology. There's actually a ton of fun fact. We're gonna go on a journey because it's just the two of us right now. Meteorology, obviously it's a ton of math in it, right? It's all about like you getting all these pressure data points, these temperature data points, you're getting all the wind data points and all that, and then you can use that to try to predict the future of the weather, right? But this led back in the day to the discovery of chaos theory, which is the coolest sounding branch of mathematics, but it's not nearly as exciting as it sounds. Because when computers were just first starting out, a guy decided, hey, hey, we're taking all these data points, right, of all this weather in my town, right, and we like understand fluid dynamics and things like that. We have formulas regarding that. So what I'm gonna do is I'm gonna put all that in a computer and ask it, what's the weather gonna be like 2 days from now, right? And he did that and he got a number. Or he did that and he got a number. He's like, it's gonna be like 15 mile per hour winds or whatever it is, right? And then he goes and he slightly changes one of the numbers because like one was wrong or something like that. And he goes, actually, wait, like over here it wasn't actually 50 degrees, it was actually like 49 degrees. And he puts it in and he gets like a totally different number. He gets a totally different prediction for what was gonna happen. He found out that if you plugged in like even a number that was like 0.001 off from like another initial condition, you would get totally different weather predictions for the future. The point being, that's weird. That's not how things normally work. Like, for example, it takes me 3 hours and 15 minutes to go from Richmond, or let's say it takes me like 5 hours to go from Virginia Beach to Virginia Tech, right, to go surfing, or the other way around, right? It takes 5 hours for me if I'm going the speed limit. If I go like 0.0, if I go like 1% higher than the speed limit the whole time, I'm probably going to get there like 1% faster, right? There's like a relationship there. A small change in the input leads to a small change in the output. Whereas weather doesn't work that way. People thought everything worked that way. It's not true at all. There are some systems, weather is one of them. Another one is population dynamics, where a very small change in the input can lead to an incredibly large change in the output. And that's incredibly disconcerting when it comes to trying to predict things, because that means that if your measurements are slightly off, your final result's going to be way off. There's like no point. And that's exactly what a chaos theory is. It's the whole like butterfly flaps its wings in South America caused a tornado in Kansas. Because the idea is a tiny change in inputs can lead to an incredible change in the output. And, it was in Jurassic Park. Cool pop culture math, whatever. It's pretty awesome. The point is that's what makes wave predicting so hard. But they nailed it this time. 10-foot waves were there, and they were incredible. I don't know how to start with this in our topic. I now kind of wish this is a chaos theory class, but it's not. I guess to start here. Any questions?
Weather's just weird. I don't know how you predict that.
Saf, if you're talking, I think we can barely hear you.
Oh, I just said weather's weird.
I think you said weather was weird, but yeah, it's very quiet.
Weather is weird, right? And I will absolutely. I'd love to talk about wave, like surfing waves. What they mean. There's there's the swell size, and then there's the seconds, and then there's the winds and all that. But anyway, Offer's here, so we could actually get started. Offer waited for you. So, so welcome, Offer. Welcome, Stava. Welcome, Herman. Let's get going. Continuing our conversation about sequences. We're taking a nice little break from like some more hardcore proof techniques like contradiction and contrapositive. And now we're talking about sequences, but don't worry. The only reason we're talking about sequences is because it's eventually going to lead to.
Professor, I had a question.
Yeah, what's up? What's up?
I was going through the homepage of our course on Canvas, and I cannot get access to written assignment 9. It says closed till November 1st, but it's due on October 13th.
That's an issue, isn't it? Wait 1 second. Thank you, Safa. Or thank you, Afra. I will do that. I will do that. I will get you that right after class. Do not worry about that. I must have just not clicked the publish button. That's okay. We'll fix it. Thank you, though. But actually, I'll write that down. Okay, but anyway, the sequences. So, like I said, we were talking about contrapositive, contradiction, and direct proofs. We're past that. Now we're talking about sequences because it will lead to something called mathematical induction, which is a way that we can prove things that we've never been able to prove before. In fact, one thing that allows us to prove is a little ditty called Euler's formula, actually Euler's criterion, which goes like this. I don't know if you've ever seen this before. Have you ever, if you look at, oh, I actually have one. If you look at a cube, right? A cube has how many faces? It has 1, 2, 3, 4, 5, 6 faces. So a cube has 6 faces. How many edges does it have? Well, it has 1, 2, 3, 4, 5, 6, 7, 8 edges. And how many vertices is it? Like how many corners does it have? And it has 1, 2, 3, 4, 5, 6, 7, 8 corners. So vertices, edges, and faces. And actually it's edges I got wrong because I forgot 4. There's 1, 2, 3, 4, 5, 6, 7, 8 edges in the top and the bottom, but don't forget the ones in the middle. There's 1, 2, 3, 4 more in the middle. There's actually 12 edges in the middle. The point is, for a cube, this is going to feel arbitrary. If you take its number of vertices minus number of edges plus the number of faces, you get 8 minus 12 plus 6, which is minus 4 plus 6, which is 2 for a cube. Let's take like a tetrahedron, which looks like this, right triangles on all sides. The number of vertices is so for a tetrahedron, the number of vertices is 1, 2, 3, 4. The number of edges is 1, 2, 3, 4, 5, 6. The number of faces is 1, 2, 3, 4. Yeah, this is gonna get us 4 minus 6 minus 2 plus 4 is 2. This actually works if you just draw like anything. You just draw like anything like right here. If you take this thing right here, this weird shape, doesn't even matter what it represents. This has how many faces? Well, actually, let's do. The point, I'm getting way off topic. The point is, it always equals 2. No matter what 3D polyhedra you pick, it could be a pyramid. It doesn't have to be a regular one. It could be a pyramid. It could be like a soccer ball shape, icosahedron, tetrahedron, any one of those D&D dice, if you're like me. All of those, if you take their number of vertices minus the number of edges plus the number of faces, it's always going to equal 2. Always. Natural question is why? Why the hell would all of these shapes are totally different, right? All of this weird invariance If you take their number of vertices minus edges plus faces equals 2. And the question is, how would you ever even begin to prove that? With the methods we have so far, basically impossible. Like direct proof, like where to even start? Contrapositive, what's it even mean? Right? Like contradiction, it's hard. But induction is going to allow us to prove this actually kind of easy. So anyway, that's what we're looking forward to. But in order to get to that, we need to first talk about sequences. Let me get John Oliver back in place. There we go. So we first talk about sequences. So we're on section 5.1/5.6, and that's weird. The book skips around. 5.1 is sequences, 5.6 is recursive sequences. We're going to do it once. It's all about sequences. So let's just remind ourselves what a sequence even is. A sequence is something that kind of goes like this, where you have just a sequence, mathematical sequence, a sequence of numbers. It goes like AM plus 1, AM plus 2, and it keeps going till you get to AN minus 1, and you finally get to AN. And all these AI here, all of these A's, they all represent numbers. So a sequence is just, well, a sequence of numbers, right? It's just kind of a list of numbers like we talked about last time. An example being, we could have 0, 2, 4, 6, 8, 10, something like that. Now, one way that we can describe our sequence here is we could say, instead of saying, well, like all of this, or sorry. One way, so one way we can write this shorthand, well, sorry, we'll get to that, So this is a sequence. And one way we can write it is like this. We can write this as, consider this the sequence of all AI, where AI here is going to equal 2 times I for all I greater than or equal to 0. So, I'm sorry. For all I greater than or equal to 0, and I less than or equal to 5. In this particular case. Why is that? Why is this saying the same thing as this? Well, because if we actually start to write this out, right, we get, okay, well, I has to be between 0 and 5. So really we could write this as for all 0 less than or equal to I less than or equal to 5. So if we actually start to write it out, we go, okay, our I is going to range between 0 and 5 as integers, right? And so we're going to start with A0, A1, A2, A3, A4, and go all the way up to A5. Now, A0 is supposed to be 2 times 0 if we follow this formula, right? A0 is 2 times 0. This is 2 times 0, which is 0. A1 is 2 times 1, which is 2. A2 is 2 times 2, which is 4. A3 is 2 times 3, which is 6. A4 is 2 times 4, which is 8. And A5 is 2 times 5, which equals 10. Am I off the screen? And so we get 0, 2, 4, 6, 8, 10. The point being that this right here and this right here represent the exact same sequence, right? It's kind of written in 2 different ways. This is kind of like a more compact way to write this sequence right here. Now you might say, well, why would I ever use this form in red over this form in blue? Like this form in blue seems like the more natural way to write the sequence. Well, the reason is, what if we're talking about sequences that have 1,000,000 values? Well, then do we really want to write down all the 1,000,000 values, or do we just want to write down what it equals and then say the range? I would rather say what it equals in the range. Or even beyond 1,000,000, what if it's infinite? For example, what if instead of it ending at 10, the sequence just kept going? Right? It went to 12, 14, but it never stopped. It went on and on and on. If it was an infinite sequence, well, then the way you represent that is that you still have AI equals 2 times I, right? It's still the same pattern, but it just doesn't stop. So it's just for all I greater than or equal to 0 now. Does that make sense? All we're talking about here is this is a different way to represent sequences rather than just writing them out. And this is called its explicit form. So an explicit form, actually formula, or form, doesn't really matter. So an explicit formula for a sequence A1, A2, or I'll start at M. AM plus 1, out to AN. An explicit form for a sequence like this is just going to be AI equals f of I for all I greater than or equal to M, where this f of I as a function that only depends on I. And by that I mean it only takes in an I. And so notice that in our example here, where we had the even numbers 0, 2, 4, 6, 8, 10, 12, 14, all the evens, our formula was 2 times I. Our function was 2 times I. And so every single term in this sequence, right, just depends on where it is in the sequence. It's just 2 times its index. We start at 0. Hope this is making sense. We're gonna do a bunch of examples to really crystallize this. But anyway, here's the point. A sequence has an explicit formula if it can be written like this, where AI equals S5 for all I greater than or equal to M. All right, so any questions? Awesome. So an example would be if AI equal to 1 over I for all I greater than or equal to 2. This is a sequence. This is the explicit form of a sequence. This describes a sequence. It's just as good as writing the sequence down. In fact, better, because this is just for all I greater than or equal to 2. There is no like upper bound on the I. That means this is an infinite sequence, just keeps going. So we could not even write it down explicitly. We could not even write it down just like normal if we wanted to. I mean, we can write down the first few and say dot, dot, dot. That's what we'll do right here. So what this actually represents is the sequence that goes, okay, so it's at I equals 2. So you have A2 is 1 over 2, right? AI is 1 over I. This is the explicit formula. This is the function right here. Then you get A3 is going to be 1 over 3. A4 is going to be 1 over 4. A5 is going to be 1 over 5. And it continues like that. So this is just, so I mean, if we get rid of the A, if we get rid of these, the sequence is just 1/2, 1/3, 1/4, 1/5, and it goes on and on and on like that. These little AIs were like those things where you draw a face, where you first make a circle, and then you draw the chin, then you draw the center line, you do that, then you make the eye, then you gotta erase all that. Yeah, it was like the scaffolding. But anyway, yeah. So this is the same thing as this. And the question we asked last time is, was this the only way that you can write this sequence with an explicit formula? And the answer? What do you guys think? Like, do you like just what's your gut instinct? Do you think that there's maybe a different formula I could use, maybe a different starting point that would give me the same sequence? Or is this the unique way? Is there a one-to-one correspondence between explicit formulas and sequences?
We could actually write it in a different way.
Yeah, exactly, Alfred. Do you know a different way at the top of your head?
It's like if we minus the second one from the first one, we get a difference, and that's the difference between all of them. So the first term minus the difference, we get the second term.
Oh, you're saying like you look at the difference here, it's going to be 1/2 minus 1/3, which is 1/6. The difference here is going to be 1/3 minus 1/4, which equals 1/12. The difference here is 1/4 minus 1/5, which equals 1/20. Can I work with that?
Yeah.
Maybe you could do something like that, and you could probably do it a slightly different way, but I don't think it would be explicit, actually. A much easier way, but you're totally right that you can do it a different way. A much easier way to do it is what if you just look at AI equals, like what if the idea is instead of starting at, so here we start at 2, right? Our first term here is A2. Then we go A3, A4, and we keep going. What if we didn't want to start at 2? What if we want to start at 1, for example? So what if we want to look at for all I greater than or equal to 1? Well, if we do that, then we want A1 to equal 1/2. But that's no longer just 1 over I, but it's 1 over I plus 1. And we'll see that this works. So if we write this out, we get that A1 now, because start at A1, is going to be 1 over 1 plus 1, right? You plug the 1 in for the I, and you get 1/2. A2 is going to be 1 over 2 plus 1, which is 1/3. A3 is going to be 1 over 3 plus 1, which is 1/4. A4 is going to be 1 over 4 plus 1, which is 1/5. And it goes on like that. So notice that we get the same sequence, 1/2, 1/3, 1/4, 1/5, on and on like that, using a different formula. It's a very similar formula, but it's a different formula. You could also do AI equals 1 over I plus 2. We start at 0. Because that would get you start at 0, you get A0 is 1 over 0 plus 2, which is 1/2. A1 is 1 over 1 plus 2, which is 1/3. A2 is 1 over 2 plus 2, which is 1/4. A3 equals 1 over 3 plus 2, which is 1/5, and it goes on like that. And again, you get 1/2, 1/3, 1/4, 1/5. Because really all we're doing, right, is if you consider f of I to equal 1 over I, right? The original way we wrote it, this is just the explicit form is f of I. You start at I is greater than or equal to 2. If you want to start at 1, you kind of have to shift everything along with it. So if you want to start 1 less, you have to shift everything. You have to kind of shift f of I over by 1 to be plugging in like f of I plus 1. The point is, right, because we're shifting the starting point 1 back, we have to shift the sequence 1 forward for everything to even out. And here we're shifting the starting point from 2 to 0. We're just shifting starting point 2 back. So we need to shift the what we're plugging into the sequence forward by 2. Does that kind of make sense? So help me out here. If I was going to start at, for all I greater than or equal to -2, what should my formula be to get the same sequence you've been getting here? So now we're shifted back from 2 by 4. We've gone 4, yeah.
I plus 4.
I plus 4, exactly, Afra. See, not that complicated, right? This shifted back 4, so we're going to take this formula here and just kind of shift it to the right by 4. Or what you plug into it, shift to the right by 4. Yeah, that's it. The point is there's different ways to write it. Any questions on this? So I hope this isn't that complicated, right? I mean, if you look at any, like, there's a lot of writing here. If you look at any individual box, right? I hope you see like, oh, I just have this formula. I just got to plug things in, and I get that done. It's not harder than that. Nothing harder than that, right? Just plug things in and you're done. We're just going to talk about some of the intricacies of things, of how there can be multiple ways to write things or anything like that. All right, how are we doing? Just good. So, and now let's talk about going the other way though, right? Because for most things we'll be doing in this class, the sequence might not be given to you, or the explicit form might not be given to you, but instead you might have a sequence, you might have to find the explicit form. So let's see how that would work. So for example, what if our sequence was, actually, let's do one more example when we have the sequence. So another example when we're given the explicit form is what if we say that AI equals sine of pi over 2 times I for all I greater than or equal to 0. Maybe we should draw a little unit circle here. So what's going on? This is 0, this is pi over 2, this is pi, this is 3 pi over 2, and this comes back to 2 pi. And then remember, this is 1, -1. In terms of height, this is 0. So sine, remember, on the unit circle is like the height. So that's sine of theta. Anyway, what we get then here is that we start at 0. Our sequence is going to be A0 is sine of pi over 2 times 0. A1 is going to be sine of pi over 2 times 1. A2 is going to be sine of pi over 2 times 2. A3 is gonna be sine of pi over 2 times 3. A4 is gonna be sine of pi over 2 times 4, and it's gonna go on and on and on like that. So first up, sine of pi over 2 times 0, what's that gonna be? It's gonna be sine of 0, right? What's sine of 0? Trig is coming back for no reason. Remember, sine is the height, and for angles down here at 0, how far off the x-axis is it? Just 0, right? Then sine of pi over 2, well, now this angle is going to go all the way up to pi over 2. So we're going to angle up to here. And now, how high is this point off the x-axis?
90 or 40, no, 45.
Remember, sine is not an angle, right? Sine's like a height. Right, so sine of pi over 2, which is the same thing as sine of 90, is just 1. Sine of pi over 2 times 2, that brings you down here. The thing keeps going down to pi. And the sine of pi is 0. Sine of pi over 2 times 3, that's going to be sine of 3 pi over 2, so it goes all the way down to here. We add another pi over 2 to it. And then that gets us, how far is that from the x-axis? Well, it's down by -1. And then pi over 2 times 4, add another pi over 2 to the angle. So we go up to here. And how far is this dot from the x-axis? Well, it's on top of it, so it's 0 away. And it goes on and on and on like this. I was hoping, so I'll tell you, what I was hoping to get this example is just plug things in, right? If to go from an explicit formula to what it actually is, just plug things in. That's all it is. Looking back on it, maybe I wish I used an example that was easier than sine. I was hoping sine would be less rusty. But anyway, I hope this tells you that you just plug it in. Like if you had a calculator, you just plug this in the calculator and you get these numbers, and that'd be fun. It's not meant to be any more complicated than that. The point of this is to go from explicit formula to written sequence. Just plug in. All right. Any questions on that? Sorry about the sign confusion. This class is not a trigonometry class. I was just trying to use it. I was just trying to use an example you might know. Maybe I chose wrong. Okay. So the point is, the more fun thing is when you have a sequence, it's like find the pattern. Oh, we have a chat. We got some chat going. Well, that's why I'd rather use it right there for you, Safa. I mean, it's kind of fun. Anyway, yeah, so. There we go. So anyway, the more fun thing to do is to go from the written sequence to the explicit formula. So for example, what if I had 1 for 27, 256. If you're watching, play along at home. I have this sequence right here, and I want to write it in explicit form. or represent this sequence with an explicit formula. What do you guys think? This is the small money round. 1, 4, 27, 256. One question you could ask is what number is next? The real question is what's the pattern? What's the explicit form? Maybe we'll come back to this one. Let's do an easier one first to show how, just show the process. So what if we had, instead of that, we had maybe, let's say 3, 8, 13, 18, 23, 28, 33, on and on like that. How would you write this with an explicit formula? So what's the pattern here? So this is Safa with the broken mic and chat. Oh, is Safa talking?
Thought it was. I thought I heard something and it was unmuted.
I plus 5. I totally see what you're getting at here, Safa. What Safa's saying by I plus 5 is what he means is notice that every time, like you just add 5 to the next one. So at 3, add 5, you get to 8. So at 8, add 5, you get to 13. 13 add 5, you get to 18. 18 add 5 is 23. 23 add 5 is 28. 20 add 5 is 33. But that's the pattern for sure, right? And the only reason it looks weird with 3, 8, 3, 8, 3, 8, 3 is because 5 plus 5 is 10. So it's going to be kind of repeating every 2, repeating the last digit every 2. But anyway, the point is, yeah, you're totally adding 5, but that's not really an explicit formula, right? What we really want to do is we want to write AI equals something, some function of I for all I greater than or equal to something. So if you add 5 every time, maybe a good starting place would be AI equals 3 plus what? If you add 5 every time, to get from 3 to 8, you add 5 once. To get to 13, you have to add 5 twice. 8, you have to add 5 3 times. So I have to add 1 times 5, add 2 times 5, add 3 times 5, add 4 times 5, add 5 times 5, add 6 times 5. Is anyone starting to see a pattern? Yeah. You do 3 plus 5i. It's all right, Safa. The chat's working just fine. So the point is, yeah, you 3 plus 5i. And where do you want I to start? Now this one we can just kind of guess and check, right? Like if we had I start at 0, or sorry, if we had I start at 1, well then we'd have their first term be A1 equals 3 plus 5 times 1, which is 8. But we don't want 8 to be the first term, we want 3 to be the first term. If we were to start at 2, we get our first term to be a2, which is 3 plus 5 times 2, which equals 13. Also no good. If we start at -1, we get a -1 equals 3 plus 5 times -1, which equals -2. Also no good. So what should our I be greater than or equal to?
0.
0, exactly, right? If we have I greater than or equal to 0, then we see we get a0 is 3 plus 5 times 0, which is perfect. We started at 3, but the very first term we want to add nothing. So that's exactly what we're doing, because 5 times 0 is 0, so we're adding nothing. And then we get a 1 is 3 plus 1 times 5. So we add 1 5 to 3, which gets us 8. A2 is 3 plus 5 times 2. So we add 2 5s to 3, which gets us 13. A3 is 3 plus 5 times 3. So we add 3 5s to 13 to get 18. And it goes on and on and on like that. So here's the explicit form given this written sequence. And as we talked about, there's infinitely many ways that we could write this if we shifted where we started back by 1 or then like shifted this up by 1 or whatever. But as long as one of them works. So for example, you could have chosen also an alternative would be if we had AI equals 3, or we could have, 3 plus 5 times I plus 1 for all I greater than or equal to -1. Or we could have AI equals 3 plus 5 I minus 1 for all I greater than or equal to 1. If you work those out, you'll see that these represent the same sequence. Let's do another one. Let's do 3, 7, 15, 31. Let's see, 3. Now I'll give you a hint. These numbers look slightly familiar to you because you guys are CS majors. Or if you're a CS major. Not presuming anything. So what's the pattern here?
Three, 7, 5. And then you have 3, 6, 9, but then these second digits would be 1, 3, 5. I forgot, but I remember this is very familiar.
Well, what do these look close to? Or maybe you start here.
Is it,
Between 3 and
sorry,
7.
is it like 3 plus 3 plus 1? And then 7 plus 7 plus 1? 15 plus 15 plus 1?
It actually works out to be that. Yeah, it does. So the difference here is 4. The difference here is 8. The difference here is 16. The difference here is 32. What are these numbers?
Multiples of 4.
Well, they all are multiples of 4, but
Or is it
some
2?
multiple 4s are missing, like 12's not here, and 20's not here.
Exponentials of 2.
Their powers are 2. Right.
Or is it 2?
Yeah, exponentials of 2, exactly, Alfred. Yeah, powers of 2. So really, I guess you could start at 3 and add powers of 2, but wait a minute. What is 3 but 4 minus 1? What is 7 but 8 minus 1? What is 15 but 16 minus 1? What is 31 but 32 minus 1? What's 63 but 64 minus 1? Right? AI here, you really think about it as equaling 2 to the I minus 1. So power 2 minus 1. The only tricky thing is, where does it start? What's our first power of 2? What should I start at?
2.
So if we have 3 here, that would mean our sequence goes, and you can always guess and check. So you add 3 here, we get A3 equals 2, 3 minus 1, which is 7. And the next term would be A4 is 2 to the 4 minus 1, which is 16. Next term is A5 equals 2 to the 5 minus 1, which equals 31. Is that what we want?
We start with 2 so that we get 2 to the power 2 equals to 4
Exactly. We want to start with 2 instead of 3. Because then we get A2, the first term, to be 2 to the squared minus 1, which is 3. Bingo. That's what we wanted. A3 is 2, 3 minus 1, which equals 7. Bingo again. 2 bingos. Rare in a bingo tournament. The point is, yes. This was a form of this, and again, you can write multiple ways. So this is kind of fun. This should be kind of fun. This is back to like elementary school, find the pattern things, you know? Ever read Highlights magazine in a dentist office, something like that? Goofus and Gallant, find the pattern. I don't know. It's fun. What's next? See, interesting enough, mathematics has a lot of patterns. And science has a lot of patterns. And mathematics starts from axioms, things you assume. Science starts from maybe first principles, you should say. Like there's the laws of physics and things like that. Like gravity, if you start with gravity, you can explain the motion of the planets. You know, like if you take gravity as like an axiom kind of thing. The point is, axioms lead to assumptions. Axioms lead to patterns. Science is about observing patterns and trying to figure out what the axioms of the universe are. Math, we kind of already have the axioms. We're kind of observing how they make patterns. It's kind of an interesting reversal. But anyway, so what if we have, we're doing kind of science right now. So what if we have, this is the first one I wrote down, 1, 4, 27, 256. So let's start here. This number 27, I think, is the key to understanding this. What do you know about 27? Just start naming facts about it.
The pattern looks like I to the power I.
Never mind with all the explanation. Exactly, Afra. Right? What I was gonna say is 27, it's like 9 squared. No, that's not right. 27 is a perfect cube. It's 3 cubed. Well, wait, 4 is 2 squared. 1 is 1 to the 1. 256 is actually going to be 4 raised to the 4. The pattern here is that this is AI equals I raised to the I power. And where do we want I to start?
1.
Exactly, 1. So here's how you go from written sequences to explicit forms. It's harder. Right? Explicit forms are written sequences, plug it in, you're done. But this, you're trying to find the thing that you can plug into to get to the written sequence. So it's a lot harder. It takes more creativity and more thinking, but it's also more rewarding. But also it's more useful because there's usually kind of hardly any point of writing a sequence out and like written like this. There's really hardly any point in writing it out like that because it doesn't really tell us much. It just is. Whereas this tells us the pattern. Like this is the written form of the pattern. It's 3 plus 5 times I. It's much more useful trying to prove anything about it. Any questions? then let's do a very special other sequence. Maybe one like this. What if we have -1, 2, -3, 4, -5, 6, -7, on and on and on. How would you write the explicit form of this? Well, let's do this first, right? If we pretended these negatives weren't here, if we just kind of look at the absolute value of the sequence, what would the pattern be? One of the simplest patterns known to man. It'd just be 1, 2, 3, 4, 5, 6, 7. And so in that case, AI would equal what? If we just had 1, 2, 3, 4, 5, 6, 7.
Would it just equal I?
Just equal I, yeah. We start at 1. So the question is, though, what do we kind of have to do to this sequence to get to this sequence? See, this sequence is, well, it's really, I mean, you could write it like this. You could write it as AI equals I if 2 divides I, and negative I, 2 does not divide I. Or you could write it piecewise like that if you remember piecewise functions. But that's very unsatisfying. If you have a piecewise function where you don't need it, it feels like a failure. There's a really easy way we could write this. Well, so I guess what do we really want to do? We want to multiply this by something. And this something we want to equal, we want this to be -1 when I is even and 1 when I is odd. Because if we have that, then we're perfect. Then we're good. Because whenever I is even, wait, I'm sorry, other way around. We want it to be 1 when I is even and -1 when I is odd. Because then notice all the odds have negatives on it. And so if this thing we have multiplied by truly is -1 when I is odd, well, that works for that. And if it's 1 when I is even, well, that gives us 2, 4, 6, 8, just like the 1. So what can you think of that is -1 when I is even, or 1 when I is even and -1 when I is odd? Why not -1 raised to the I? Because then notice, -1 raised to the I when I is even, -1 squared, for example, is 1. -1 to the 4th is 1. -1 to the 6th is 1. -1 raised to an even is 1. And conversely, -1 raised to an odd is -1. This is a fact about -1. So if we write it out, we get A1 is -1 to the 1 times 1. -1 to the 1 is -1 is -1. A2 is negative 1 squared times 2, right? Just plugging in this formula. Then we get negative 1 squared is 1 times 2, which is 2. A3 is negative 1 cubed times 3. Negative 1 cubed, negative 1 times negative 1 times negative 1. That's going to be negative 1. This is negative 3. A4 is going to be negative 1 to the 4th times 4, which is going to be 4. It goes on and on like that. And you notice we get exactly what we wanted to get. Does this make sense? Got a tentative nod from Herman, so we're gonna go with that. Yeah, totally. Yes, I think it makes sense. This totally makes sense, right? This is what negative 1 does. Negative 1 raised to a power, if you guys remember calculus and series and sequences from that, negative 1 raised to a power alternates. It goes negative 1, 1, negative 1, 1, negative 1, 1, negative 1, 1, negative 1, 1. And so that is exactly what we're taking advantage of. And this is exactly an alternating series. I'm sorry, not series, sequence. Alternating sequence. Alternating sequence, by definition, is a sequence that alternates from negative to positive in every consecutive term. So, for example, we could have one minus 4, 9, minus 16, 25, minus 36, 49. Right? Just alternates positive, negative, positive, negative, positive, negative, positive. And the way to find an explicit form, or formula, to find explicit formula, first find formula for the absolute value of the sequence. And then here's the fun part. Here's what makes it alternating. Multiply by negative 1 to the k, or negative 1 to the k plus 1, depending on how your sequence starts. And I'll write here, no shame in guess and check. Here's what I mean by this. So we'll end in a second. So 1, negative 4, 9, negative 16, 24, negative 36, 49. First consider the absolute value of the sequence. So get rid of the negatives. That's going to be 1, 4, 9, 16, 24, wait, this would be 25. There we go. 36, 49, on like that. And what's the explicit formula of this?
I square?
Exactly, for I squared for all I greater than or equal to
1.
Exactly, starting at 1. Now,
I think I figured it out.
what's it gonna be? Alpha wants to solve the puzzle.
-1 to the power I multiplication I square.
So this is close. And here's where the no shame in guessing check comes in, right? If this is our explicit formula for all I is greater than or equal to 1, right? Then what we get is we get the sequence, we start at 1. A1 is -1 to the 1 times 1 squared, which equals -1 to the 1 is -1.
Then my power is I plus 1.
Exactly. Yeah, exactly. That's all it is. You try it with with a -1 raised to the I. That doesn't work. Try with -1 raised to the I plus 1. Right? It's a guessing check. And now this will work. It all depends on where it starts. So here we get A1 is -1 to the 1 plus 1 times I times 1 squared, which equals -1 to the 1 plus 1. That's -1 to the 2. -1 squared is 1 times 1 is 1. Then we get A2 is -1 to the 2 plus 1 times 2 squared. -1 to the 3 is -1 times 2 squared is 4, -4. A3 is -1 to the 3 plus 1 times 3 squared. -1 to the 4, -1 to an evens, always going to be 1 times 3 squared is 9. And it goes on like that. The point is this successfully recreates our sequence. So we'll do more of that. Tomorrow. But the point is, this is the idea. First, do it with the absolute value, take away the negatives, and then either multiply by -1 to the I or -1 to the I plus 1. I put K here. The point is, the index doesn't have to be I. You could use K or J or M or M, whatever you want to use. But the point is, this is the idea. Any questions, anybody? Okay, then since for all people in the Zoom call, there are no questions, I mean, there's not exist anyone with a question. So I can successfully rest tonight. Then that is sequences. We'll do a little bit more with that tomorrow. And then we're on to induction. Gonna start proving some cool things. Not that we haven't already been proving cool things. I feel like this class always ramps up. I mean, this is the nature of math, never being satisfied, always moving on. It doesn't matter that math exists for 2,000 years. You've already proven 1,000 incredible things. But there's more things to prove, more techniques to learn, more fields to open. Yeah, so it's fun. I like it. The second one, homework 8. Which one? What was that?
Seller and the ghost one.
Oh, right, exactly, Safa. Yes, that is what contradiction is. That I'm so glad you said that, right? I made that example to try to give you guys that feeling. Now, it's like, it makes more sense, maybe, that feeling, if you apply it to like a murder mystery example, where it's like, if you assume it's the gardener, it actually turns out it can't be the gardener. It actually turns out you get this weird contradiction, and it wouldn't even make any sense. Right, so it can't happen. That's a great way to prove something. It makes you feel so good. It makes you feel like you trick people into something, but you did. But once you start seeing the matrix like me, you start seeing math for what it is. You get that same feeling when you do it for math too. But anyway, the point is, I will be happy if by the end of this class, first of all, everyone passes and does well and is successful and likes the class. But I'll be even happier after that if you guys just start to get the general feeling of why math is cool. Like if you see a guy on a chalkboard enjoying some math, you go, I kind of get what he's doing. I kind of get what's going on there. But anyway, that's it for the class. So have a good day, everybody. See you guys when I see you. Even if you have any questions, have a good one.
Thank you, Professor.
You're welcome, Alfred. Thank you.